You can't see it? Is? Okay, we're good. It's more to do with the phraseology of this question, but that, I mean, they're asking you to find the partial derivative with respect to x. And here they're asking you to find the partial derivative with respect to y. If you think about that surface that I was talking about, imagine this is the surface that represented that guy. If you take a slice of that shape and you do it in the x direction, then you do it in the y direction, what you're basically doing is you're drawing a line something like this, and then it's cutting that shape. And can you imagine if you cut that shape, you'd end up with this fella. And what you're trying to do is find the derivative at that point. So what they're really saying here is just find these two guys' partial derivatives, and then plug in that x and that y to the answer. So let's look at the process of how you would find these two different partial derivatives. Now, there are two ways to do this guy. Both end up being the same answer, but there are two ways to do it. You could think of this as being f, you can think of this as being g. And if you wanted to find the partial derivative, let's say we do this one, then this would become the quotient rule. But a special version, partial derivative version of the quotient rule. The top is 94. Now, since we're differentiating with respect to x, this fella, instead of really being called f dash x, truly should have been called f subscript x, right? The partial derivative with respect to x is 0. The bottom guy is 7 plus x squared plus y squared. And instead of really calling it g dash, you see I'm going to call it the partial derivative, which is the equivalent to that. But that's a number, and that's considered the number, so all you get out of that guy is this. So you can, if you do it this way at least, you can say f dashed, which is 0, times g. I don't even need to write g down because I'm going to multiply it by 0. Take away f times g dashed, and the whole thing is going to be over 7 plus x squared plus y squared. Now that gets you nothing. This guy gets you 188 over that guy. Now we're going to evaluate this at the point, I believe it was the point 23. So can you imagine I found that guy goes there, 7 plus this guy, and then I'm just going to assume that if I can get back to my guy, that fella there simply just turns into that ugly number I had a minute ago. Now I'm frantically trying to find the stop sharing screen. Oh, it's not shops. That's why. Here we go. Right, did that make sense? Let's go back and check what the answer is. Right, so one of those answers is negative 47, and the other one of those answers is negative 141. Right. Now, if you're doing something in the x direction, right, so you're doing a slice that's parallel to the x-axis, can you see what you're doing there? Is you're picking like y equals 1 and doing a plane parallel to it, or y equals 2. So you're finding, you're assuming that y is a constant. So that would be the derivative with respect to x is the x direction. The derivative with respect to y would be the y direction answer.
So on your paper, you show
Yes.
when you go from the symbolic f prime g minus fg prime over g squared.
Yes.
You're not showing the g squared underneath. It's just,
Oh, that's because I forgot to.
okay.
It should have been there. And I'm assuming that when you plug in the numbers, there'll be a little bit of cancelling. You know, so it'll be divide top and bottom by 10 or 40 or something, and that's why the answer is a little bit smaller looking than these would. Now, that's actually the beginning of directional derivatives. So when you're looking at these functions, try and think of them as x, y is the floor, and z or u or t, whatever the variable is your vertical height. And you're looking at a kind of curved surface. And so when you're doing partial derivatives, you're taking that surface and getting like a knife and cutting it parallel to the x-axis or parallel to the y-axis. And when you do that cut, do you see that all you'll now see is a two-dimensional curve? And the partial derivative is the slope of that curve at 2, 3 or whatever the point happens to be. Later on, that's going to be... Let's suppose I want to find the partial derivative of z with respect to x. What I see here are two different places with x's. And these two things are clearly multiplied. So that tells me that if I want to find the partial derivative with respect to x, I'm going to have to do the product rule, which is fine. Now, this is the product rule the way it is written in Calc 1, but it's a good placeholder for what we're going to do. In this case, f is going to be that guy, and g is going to be that guy. So that's what you'd expect. The derivative really should be called that guy again. Now, if you differentiate that guy, you get 1, with respect to x, of course. Now, if you differentiate this guy with respect to x, don't think of this as the sine of xy. Think of this as, well, I don't know, the sine of 5x or the sine of 10x. Think of y as being a number, right, a constant. Now, when we differentiate the sine of 2x or 5x, you would get the cosine, right, of 2x or 5x. But wouldn't you also get the derivative of 2x or the derivative of 5x? In this case, the derivative of yx. Right? If you differentiate that, do you see that you get an extra y? That's where that's coming from, right? So if you differentiate with respect to x, partial derivative, the sine of xy, you get the cosine of xy times the derivative of xy, which is just y. Now, if I put these pieces in, this guy's 1, leave that guy alone. This guy is x, and the derivative is y, cosine of xy. And mine are tidying up. You never write 1 times something, and that's it. And just to show you that partial derivatives don't always end up being the same working when you change the variable. When I look at this question and I'm thinking, okay, I want to differentiate this thing with respect to y, do you know that x is a constant? It's like 5 sine of 5y or 10 sine of 10y. You see, the x is a constant. So I don't have to do a product rule. In fact, it wouldn't make sense to do a product rule. All I would do is differentiate this thing, right? Essentially a little chain rule. You'd get x, the cosine of xy, times the derivative of xy with respect to y. So if you differentiate xy with respect to y, you just get x. And so this guy becomes x squared, the cosine of xy. So we're adapting the product, and earlier on today we did the quotient rule. We're adapting it to a multivariate situation. So it's essentially the same formulas, the same rules, but the adaptation is that it's not really f dashed, it's the partial derivative with f with respect to x, or whatever the variables happen to be called in this situation. And you have to adapt your product and your quotient, and technically even your chain rule, as I was doing here, to take care of that. Are we good? I seem to have lost someone. Okay, I'm trying to get back to myself now, which is a little bit strange. Okay, where am I? I have disappeared. Okay, has anybody else got another question? I'm just going to keep it like this for the time being until I figure out why I can't find myself. I assume you have two versions of me, but not the one I'm looking for.
For the chain rule part, is it just we multiply by the derivative of x?
Okay, let's do an example of a chain rule unconnected to this question. Suppose I had z equals x e to the x squared y, right? And I was wanting to find the partial derivative with respect to y. Well, the way my brain would be working is, can you imagine it was z equals 5e to the 25y, right? Imagine x was a number, I'm just randomly picking 5. This is how you would work with in Calc 1, and this is how you're going to deal with it now in Calc 4. The chain rule comes because of this. Now, if you wanted to differentiate this fella, right, with respect to y, you would get 5e to the 25y times the derivative of 25y. Well, the derivative of 25y is just 25, and then off you'd go and you get your answer. In this case, you get x e to the x squared y times. Now, what's the derivative of x squared y with respect to y? That's the part where the chain rule comes in. You get x squared. And then if I tidied this one up, it looked like that. But in case you're into the habit of, well, you really just have this extra bit added on and that's it. Here's a situation where that wouldn't work. Suppose I had to do e to the xy cubed, and I wanted to find that partial derivative. It would be e to the xy cubed times the derivative of xy cubed with respect to y. Is that guy. Do you see you get a lot more than just the x? So that's a chain rule situation. Did that help?
Yeah.
So think of what you did in Calc 1 with chain rule, and just bear in mind that there's going to be variables that are treated as constants. There are going to be x's or y's that are now going to be treated as constant. But the other variable, whatever the thing you're differentiating with respect to, that's still a variable, and the rules governing that don't change, right? The derivative of x cubed is still 3x squared with respect to x at least, right? Have we any other questions?